Okay, so welcome to the Homotopy type theory electronic seminar talks. If you're watching this on YouTube, I encourage you to join us live next time. That way you can ask questions and participate in something happening right as you watch it. So this week I'm pleased to introduce Andrew Swan from Carnegie Mellon University. He will be speaking about choice, collection, and covering in cubical sets. Okay, go ahead, Andrew.
Okay, thank you. Okay, so I'm talking about certain principles that I'm going to call choice, collection, and covering principles, how they behave in cubical sets, and specifically how they fail in the presence of an axiom called Brouwer's principle. So I'm just going to start by defining Brouwer's principle. So this says that all functions from Baire space n to the n to the naturals are continuous. So explicitly, this says that, explicitly a function f from n to the n to n is continuous if it somehow only depends on finitely much information from the function alpha. So for any point alpha, there exists a natural number, n, such that for any other function beta, if beta agrees with alpha up to this finite number n, then f of alpha is equal to f of beta. So this is, of course, a anti-classical axiom. So it's false if you assume it's the law of excluded middle, but it's consistent with many systems of constructive mathematics. So we can kind of consistently assume it. So then the result is that we work in a meta-theory, one of these consistent theories where Brouwer's principle holds. And in this case, certain principles are false in cubical sets. So specifically CCHM cubical sets, but I think also these arguments should work, some of these arguments will work more generally for like other variations. So first of all, choice principles hold. So there's a weak form of countable choice due to Martin, Escardo, and Knapp. Another weak form of countable choice due to Bridges, Wichmann, and Schuster. And finally, yet another weak form of countable choice called ACN2. So this is kind of saying that every multi-valued function from n to billions has a choice function. Okay, next, covering principles. So these talk about there being a cover or a kind of surjection to certain types. So there's an axiom that you can assume that says that every type is covered by an hSet, and as a specific instance of this, you might, so one specific instance is to look at a particular type, the product of countably many circles, and I kind of think of this as the simplest place where sets covering can go wrong. And this is kind of saying that, well, in cubical sets, in this meta theory where Brouwer's principle holds, it kind of does, well, it's false in any case. And also in cubical sets, you have a notion of constant cubical set. And it's also false that every hSet, in the sense that it's internally an hSet in homotopy type theory, is covered by a constant cubical set. And final one is collection principles. So collection and fullness. So these axioms come from set theory originally, but there are also kind of more type theoretic versions based on, so these have also been formulated in category theory, in algebraic set theory, and you can kind of also look at these versions in type theory. And finally, there's an axiom called WISC, or weakly initial set of covers. Usually I would count this as a choice axiom, but for the purposes of this talk, I want to include it as a choice axiom. So yeah, so I wanted to start by defining these notions. So first of all, we remember that working internally in homotopy type theory, a map is a surjection if every fiber of the map is merely inhabited. So in other words, we express it as this type here. Sorry, this one here. And I also say that the pair consisting of the type B and the surjection is a cover of A. And we say that A is projective if every cover has a section. So yeah, so by section I just mean a map from A to B, such that F composed of that map is the identity on A. So it's kind of yeah, kind of chooses an element of each fiber, if you like. And so we can express the axiom of choice as saying that every type is projective. And then we can also look at specifically countable choice, which says that n is projective, for example. Okay, so some more choice principles. So yeah, so I wanted to focus on a choice principle due to Martin Escardo and Knapp, because, well, okay, so it's a very weak version of countable choice. It kind of holds in a lot of settings, but that's not the only reason. Like, so somehow this is a typical example of the kind of thing which is false in cubical sets when you assume Brouwer's principle. So this is kind of somehow the key to like understanding the kind of thing that's going to fail and like why it fails. So in order to state this, we use n infinity. So so I learned about this definition from Martin Escardo. I'm not sure where it came from originally. If we're given a binary sequence, so a function from n to 2, then we write these brackets alpha for the type of n such that alpha n equals 1. And then we define n infinity to be the collection of those binary sequences where this brackets alpha is an H proposition. So what this is saying is that alpha is 1 at most once. So it's always or almost always 0 somehow. So as a special case, for every n, we can construct an element underline n of n infinity by just saying it's 1 when, so we need to define a sequence. So we define it for every natural number m, and then we say it's 1 when m equals n, and otherwise it's 0. So it's 1 exactly once. So so this type is an H proposition. And also, if we Also, the constant sequence, which is 0 everywhere, this is also a proposition because it's always because it's empty. And so that's another point of n infinity. And then we denote that as infinity. So in classical logic, this is just kind of the natural numbers with like an extra point added. But in constructive mathematics, there's a kind of, that's not necessarily a good way of looking at it. So we have these natural numbers in, and then we have the point n infinity. But if we're given an arbitrary element of n infinity, we have no way to kind of distinguish these two cases. So if we're given a sequence, and then we kind of look at some initial segment, and we only see zeros, then we have no way of knowing whether it's just going to be zeros forever, in which case it would be infinity, or it might be that it's zeros so far, but like sometime later on in the distant future, there will be a 1 somewhere, in which case it will be n underlined for some very big n. And a kind of more formal way of phrasing this is using continuity. So we suppose we're given a continuous function from n infinity to 2. So this is continuity with respect to the subspace topology from Baire space. Yeah, so we're given this continuous function, then there is some n such that for sufficiently high, so for n greater than n, the f at n agrees with f infinity. So for sufficiently high n, fn is equal to f infinity. And so this is particularly powerful when you combine it with Brouwer's principle, because it follows from Brouwer's principle that every function at all from n infinity to 2 is continuous. So this proposition applies. So and then so then Martin Escardo and Knapp used this to formulate a certain axiom of choice, which I'm going to call Escardo-Knapp choice. And this says that for every alpha in n infinity, this brackets alpha is projective. So yeah, so if you assume the law of excluded middle, then either alpha is equal to infinity, in which case this is empty, which is a proposition, or alpha is equal to underline n for some n, and in that case this is equal to 1, and these are both of these are projective. So in the presence of excluded middle, this is true. And also, if you don't want to assume the excluded middle, you can also derive it from countable choice. Yeah, so I don't think I'll prove this, but this is also possible to derive it from countable choice. And in fact, you can use a weaker version of countable choice due to Bridges, Richmond, and Schuster.
Andrew, can I ask a question? So it's Dan. How would this differ from just assuming that all H props are projective?
So it's a special case of that.
But it's not equivalent? I mean, you can't get any H prop as one of these alphas?
Yeah, so I think in general there can be examples of H props that can't be written, because I mean you have to like for that to be true, you'd have to like take an H prop and find some kind of binary sequence that it's like equivalent to. So I don't think that's possible in general.
Okay.
Okay.
Is it strictly weaker than choice then?
Sorry, can you say that again?
Can you hear me correctly?
Yeah, you're a bit quiet, but yeah.
Can you hear me now?
Yes, that's better.
All right. Is it weaker than choice in the sense that if you have choice, you can't, no, sorry, if you have EKC, you can't prove choice?
That's right. It's weaker than choice.
Okay.
So, for example, you can derive it from the law of excluded middle. So if you take some model where excluded middle holds but not choice, then EKC will still hold. Okay. Does that answer the question?
Yep, that's fine.
Okay. Okay. So yeah. So I also wanted to define one more choice axiom. And
there's also a question in the chat quickly.
Oh yeah. Can't see the chat.
It's a question from Jonas.
Yeah.
He's asking whether semi-decidable H-props are projective.
Semi-decidable. Yeah, I think you can interpret it that way. Yeah. I think that's an okay way of looking at it. Sorry. Okay. So right. So for the next version, so for the next choice axiom, I want to talk about multi-valued section. So we're given a family of types B from A to U. So a multi-valued section is, first of all, we have a proposition which takes an element of A and an element of BA, and then returns the proposition, together with a proof that for every A there exists some B such that PAB is true. So this is kind of, so a section would kind of pick exactly one B for every A, and this is saying we have some like inhabited collection of B's. And it's also possible to express this more diagrammatically using the version from algebraic set theory due to Benno Vandenberg and Ika Moerdijk. So a multi-valued section. Well, okay, so first of all, instead of a family of types, we just have a function where the fibers of the function are the dependent types. And then a multi-valued section is an embedding from just any type P into E, such that the composition with F is surjective. So this is just a kind of cleaner, more diagrammatic way of stating the same kind of thing. And then as a special case of this, we can talk about multi-valued functions. So instead of looking at arbitrary families of types, you can just look at the constant families of types for A and for two types A and B. And then so kind of diagrammatically, a multi-valued, so diagrammatically we have this kind of projection map from A times B to A. And then we have a multi-valued section of the projection map is what we call a multi-valued function from A to B. So instead of having exactly one element of B for every A, we have a kind of inhabited collection of B's for every element of A, merely inhabited. Yeah. So, and then we can use this to state the axiom of choice for multi-valued functions from A to B. And this is saying that if we have a multi-valued section, I, then we can refine it to a single-valued section. So a single-valued section is just, well, okay, so it's a function from A to B, but If you're given a function from A to B, you can also view it as a multi-valued section where this map into A is an equivalence. So I just kind of wrote it as the identity on A. And then the axiom of choice from A to B says that we have a map here from A to P. And so in particular, we can look at the axiom of choice from the natural numbers to the Booleans. And so this is kind of interesting for me because it holds in realizability models. So before I worked in homotopy type theory, I kind of looked at realizability a lot. And so I was kind of used to the fact that ACN2 is something which nearly always holds, like for free. Like you don't even have to assume it in the meta theory. It just kind of holds in models for free. And also it's another principle which follows from the law of excluded middle. So also in classical mathematics, it's something which is just true. So I mean, there are models where it doesn't hold. So for example, in topological models over, so a typical standard example would be sheaves over the unit interval be one where it model where it fails. Okay, so now covering principles. So we say that X is covered by a set if there exists a cover Y and a surjection to X where Y is an hSet. And so there's an axiom, I'm not sure where it came from originally, but there's an axiom that says that sets cover if every type is covered by an hSet. So yeah, I think this is maybe something which holds in simplicial sets if you work in a classical meta theory. I'm not sure about that though. But at the very least, you might expect that at least there were a few concrete examples which are covered by hSets. So so if you have any inhabited connected type, then it's kind of covered by a map from 1 into the point. So for example, S1 like has to be covered by an hSet. And it's kind of also the kind of class of types covered by hSets is somehow closed under like standard under most standard constructions in homotopy type theory. So for example, it's closed under push-outs and under like finite sums and things. So kind of, I think the kind of simplest example of an operation which doesn't have to preserve sets which are covered by hSets is products. Okay, and but if you have a product of hSets, then that is itself an hSet, so it has to be covered by an hSet. So kind of the simplest example I could think of, which kind of doesn't have to be covered by an hSet, is where you take the product of infinite many copies of a one type, and the simplest one type that I know of that isn't a zero type is S1, the circle. Okay, so this is kind of the simplest thing, which kind of doesn't have to be covered by an hSet. But if you assume countable choice, then it is. So so we have a map from 1 into this type, which just sends every natural number. Well, so it's a constant map which takes a unique element of 1 and then returns the constant function from n to S1, which is just the base point everywhere. So that defines a map from 1 to the product of circles. And then, so if we can show this map is surjective, then we're done. And in the presence of countable choice, we can do this. So we're given f in the product, and then we need to find an element that f so we need to show that there exists a function which assigns a proof of fn equals base for each n. Since S1 is 1 truncated, we know that Sn equals base is an hSet. So we've got countably many hSets. And since S1 is connected, we know that each of these hSets is merely inhabited. So we can apply countable choice to kind of get this one. Okay. And then so now I'll move on to onto collection principles. So collection principles are somehow used to show that so they don't imply choice, but they somehow say that choice doesn't fail so badly that it causes certain size issues. So kind of choice doesn't make things kind of, so the failure, if choice fails, it doesn't make things kind of explode and get kind of too big and kind of cause size issues. And so I wanted to talk about collection and fullness and and this weekly initial set of covers, which I'm going to include for today, just for today, as a collection axiom. So all of these are stated using the notion of weak initiality. So we're given a category and we're given a collection of objects in the category, which I want to think of as a type I and then a function from I into the objects of the category. And then we say that this function, this collection of objects is weakly initial if for any object in the category, there merely exists I in the indexing set and there merely exists a morphism from xi into y.
Andrew, does it matter what kind of categories exactly you're dealing with? Like, are you assuming that things are hSets or that they're univalent or anything like that?
So I guess this definition works with the kind of most basic one. So it's what I call like wild category, where you don't have any kind of axiom at all. But in all of the examples I talk about, that they're always kind of very concrete things where you kind of don't have to worry about the difference between definitions so much.
Okay, thanks.
Okay, so I realize that I haven't defined this notation yet. So what this is saying is that we can view the collection of covers as a category. So so if I kind of flip back to the definition of cover, so if I flip back to the definition of cover, we notice that in particular it's a map from a type B into A. So it's a, in particular it's an object of the slice category over A. So we can view the collection of covers as a category, as a full subcategory of the slice category over A for fixed type A. But then we notice that this is a bit ambiguous, because when we talk about types, we need to specify which universe we're working in. So kind of a natural assumption might be that B has to lie in the same universe as A, but you might kind of also think about what happens when you go to the next universe up. And in that case, you can have covers of A, which are kind of appear in the next universe up from where A appears. So this is kind of the explanation for the kind of notation I used here. So, so we're given a type X in the universe U0, say, and then we write cover 0 for the covers where the domain of the cover is also in U0, so at the same level as X. And then we write covers at 1 for the category where the covers are where the domain of the cover is allowed to appear in U1. So it's allowed to be one level higher than X. So the axiom of collection, so this is kind of, yeah, so again, this is a type theoretic version of collection based on the algebraic set theory definition. And so what it says is that this inclusion from covers at level 0 to covers at universe level 1 is weakly initial. So when we go up a level and talk about covers at universe level 1, well, it has to add some more, but this is somehow saying that it doesn't add too many more. So whenever we have a cover at level 1 of a type at level 0, we can find some cover at level 0 which somehow approximates it. So there needs to be some map over X. Okay. So similarly, we can talk about the axiom weakly initial set of covers. So this is a kind of related axiom, and this is saying that, well, instead of looking at how things change from when we go from universe level 0 to universe level 1, we're saying that covers at universe level 0 is already somehow, we already have some kind of bound on it. So we have some set of covers. So this is a type I at universe level 0, like the same level as X. And then we have a family of covers of X indexed by I. And yeah, and then WISC says that there exists such a map such that this is weakly initial. So we can find some kind of small collection of covers such that every cover can be approximated in a certain sense by covers in the collection. And then finally, the axiom of fullness. So yeah, so this talks about multi-valued sections. Yeah, and again, this is the this is based on the algebraic set theory definition due to Benno van den Berg and Nika Moerdijk. So we note that the axiom of choice says that the map from dependent functions, so if you have a dependent function, then we can view it as a single valued, multi-valued section. Yeah, sorry, this slide is actually wrong. Oh, no, yeah, sorry, it is correct, it is correct. Choice is equivalent to saying that this inclusion is weakly initial. And the axiom of fullness says, okay, what if we weaken this, and instead of saying that this specific map is weakly initial, we just say that there is some type, and there merely exists some type, and there merely exists some map I into multi-value sections, which is weakly initial. So this is somehow a kind of weaker version of, well, okay, so it's a weaker version of choice, first of all, but it also follows from propositional resizing, because in the presence of propositional resizing, the collection, so a multi-value section is in particular an embedding from a type P into E, and then in the presence of propositional resizing, this is a small collection. We can just kind of look at the collection of all embeddings from P into E, and then this is small in the presence of propositional resizing. And then we can just take this to be an identity map. So that's why it follows from propositional resizing. And so the kind of thing that fullness is used for is we're working in a setting where both power set and choice fail, and then we want to show this doesn't cause size issues. So we want to show the Dedekind reals still form a small set, for example. Yeah, so usually these axioms are very easy to satisfy. So the kind of origin of the fullness axiom, and well, at least the set theoretic formulation, and the kind of reason why collection is included in constructive set theory is that they hold in Peter Axel's interpretation of constructive set theory into type theory, and you don't even need to assume that they hold in the background universe, so you just kind of get them for free from the way that interpretation works. And then for similar reasons, these also hold in setoids for free. And also in the kind of algebraic set theory setting, they're kind of preserved by kind of typical topos theoretic constructions. So things like sheaf toposes and realizability toposes and size toposes all preserve these axioms. Well, okay, they preserve WISC, fullness, and collection. Definitely not countable choice, but kind of the collection principles are like so kind of harmless that they are preserved by sheaf toposes, and as well as like other constructions. So it is known that all of these things are independent of. So it's known that so there are kind of topos theoretic constructions to where they can fail, where you kind of go beyond the usual definition of sheaves and like allow kind of large cardinals to play a role, or proper classes. And also in set theory, it's kind of known that these things are independent, but it's kind of very difficult proofs. So you can prove that WISC is independent of ZF using a very using kind of some fancy forcing techniques due to Gittic, and a kind of later version, more recent version by Asaf Kara-Vila, which doesn't use large cardinals, but does use class forcing, which is also kind of quite a technical technique. Again, there's the proof by Friedman and Shedrov that collection is independent of constructive set theory, and again, this is kind of quite a fancy proof. Yeah, and again, for fullness, there's a proof by Bob Lebowski that it's independent of CZF, where fullness is weakened to exponentiation. And in order to do this, he kind of invented an entirely new kind of forcing that he called forcing with Seslin. And it can also be proved using realizability, but again, this is kind of quite a bit of a tricky proof as well. So, yeah. Okay, so now what about cubical sets? So, yeah, so as I said at the beginning, I wanted to kind of keep things simple. I want to talk about a specific version of cubical sets. And then, so to pin it down, I talk about the kind of CCHM model, the Cohen-Kocan-Huber-Mortberg model. So we just say cube category, we take n to be the set of objects, and then a morphism from m to n is a homomorphism from the 3 De Morgan algebra on m elements to the 3 De Morgan algebra on n elements. And then cubical set is a covariant presheaf on this category. So it's a functor from the cube category to sets. And then, so Cohen-Kocan-Huber-Mortberg showed that these form a constructive model of homotopy type theory with an emphasis on constructive. And so because it's constructive, you can carry out in a meta theory where Brouwer's principle holds. The kind of thing that I keep in mind is like models of set theory where Brouwer's principle holds. But there are like other approaches as well. So maybe this could also be done in extensional type theory, for example. Okay. And so a key point that I want to make about this model is how propositions, how H propositions behave in the model, and how propositional truncation behaves in the model. So kind of just to remind ourselves how it works in extensional type theory. In extensional type theory, in the where it has models in locally Cartesian closed categories, and in this setting, a type in context gamma is just a map. Well, okay, a context is an object, and a type is a map into the object. Terms are sections of this map, and in this case, two terms are propositionally equal only if they're equal externally as maps in the LCC. And then because of this, a type, if a type is an H proposition, then it has at most one section. So then when you take propositional truncation, it has to somehow strictly identify points together. And so somehow like erases all the structure of the type. And then, yeah, so I just emphasize that point. And then in the CCHM cubical sets, so this is true in many other homotopical models, so it's already true for simplicial sets. It's kind of true in general for Orton-Pitts models of cubical type theory, so this includes CCHM cubical sets as a special case. So we have some kind of interval object. So this is just an object I together with two what we call endpoint inclusions, delta 0 and delta 1 from 1 into I. So typically this will satisfy other conditions. So usually, well, okay, so in all the homotopical models I know of, these have to be disjoint. These endpoints have to be disjoint. Okay. And then we can use this to define points, paths, and homotopies. So a point of a cubical set is a map from 1 into the cubical set. A path in a cubical set is a map from the interval into the cubical set. And then a homotopy between two maps is a map H from I times X into Y, such that if we compose it with one endpoint, we get F, and if you compose it with the other endpoint, we get G. So, right, so in cubical sets, kind of in contrast to LCCs, a type is not just a map into gamma, but it also has some extra structure that we call a fibration structure. Terms are interpreted as sections, just like with extensional type theory. Okay, but now two terms are propositionally equal only if they're homotopic. So they don't have to be equal, they just have to be homotopic. So an H proposition can have many different sections as long as they're homotopic. So they don't have to all be equal, they just have to be homotopic. So then propositional truncation, it keeps 2 points separate, but adds a new path between them. So it somehow doesn't erase the structure of a type. It's somehow still there. It's just added even more stuff on top. So this observation has come up before. So it's kind of related to a kind of impressive. So there's a nice result by Nikolai Krauss that this is somehow even true syntactically in homotopy type theory. But then the kind of the semantic property is something that I used before in some joint work with Taichi Umura. So we showed that use these kind of ideas. So Church's thesis does not hold in cubical assemblies. In this, so there's a kind of general definition of high inductive types due to Khan, Huber, and Mortberg in these CCHM cubical sets. So you define it inductively. So first of all, if X is in the original type, then we add it in to the truncation. Okay. Secondly, we freely add a path between any 2 points of the propositional truncation. And then thirdly, we add some other stuff for technical reasons. So in order to kind of make the proposition fibrant, we have to add these extra hcomp elements. Okay, so like in a way, the important thing is this SQ. This SQ stands for squash. So we add squash terms, and then these are kind of paths between any 2 points that we add kind of freely as part of the inductive definition. And then we can also look at another inductive definition where we kind of remove the interesting part, these squash terms, and then we just look at the stuff which is kind of free, which was just added for like technical reasons. So, so we call this local fibrant replacement. And then, so it contains an element. So for every element X of the original type X, we add that to the local fibrant replacement. And then we also add this stuff, which was all these hcomp terms, which were added for like technical reasons. And then we can, so then we can factor the truncation map as first a map into the local fibrant replacement and then into the truncation. All of this taking place in a slice category over a fixed gamma. And then you have some nice properties. So actually, I'm gonna skip over the kind of concrete definition and give like a nicer kind of categorical version of that. So, right. So we have this picture where we have an X here, and then we have the truncation over here, and then we have a truncation map, and then we can factor it through the local fibrant replacement, and then both of these maps are monomorphisms. And then the local fibrant replacement has a nice property that it's that it's equivalent to the original type X. So I is a homotopy equivalence. So it has a homotopy inverse R, like this. This gives this diagram. And then it has some nice properties that you can, yeah, okay. So, yeah, so if we have a map A into the truncation, we say it's squash-free if it factors necessarily uniquely through this inclusion of the local fibrant replacement into the truncation. So the reason for the name squash-free is that this is kind of the version where we removed all of the squash terms and just had the other stuff. Yeah, so we say a map is squash-free if it factors through local fibrant replacement. And in this case, we can define a map T bar by composing it with the homotopy inverse of the inclusion from X into the local fibrant replacement. So we call this map T bar, and we call it the detruncation of a squash-free map into the truncation. Yeah, so kind of I skipped over the kind of technical, kind of type theoretic version of a lemma earlier, and I'll just show you the kind of nicer kind of category theory version. So any map from the terminal object into the truncation is squash-free, and for any representable object, any map into the truncation is either squash-free or it's not squash-free. So in classical logic, this would be trivial, but in the presence of Brouwer's principle, it's kind of very powerful because it allows us to define a function into Booleans, into two. And then Brouwer's principle says that if you have a family of things, a family of maps indexed by Baire space, then this kind of defines a continuous function from Baire space into two. And then also by diagram chasing, we can show that there's a kind of naturality condition. That if we have a map T from A prime into the truncation and another map H into there, then the detruncations, well, first of all, if T is squash-free, then so is the composition, and then the detruncations kind of match up nicely as you would expect, just by some kind of diagram chase. And then if we apply this to paths, in cubical sets, the interval object is representable, so we can apply the kind of above remark to show that any path in the truncation is either squash-free or not squash-free. So there's plenty of examples of paths which are not squash-free. So if you have any 2 points in the truncation, you can use the squash terms to make a path, to make a homotopy between the 2 points. And kind of by definition, that's not going to be a squash-free path. But there's also examples that are. So if P is a degenerate path, so this means it factors necessarily uniquely through the terminal object. In that case, the path has to be squash-free. And also, because I is representable, any path is either squash-free or not squash-free. So we can use this to kind of get well-defined maps into the Booleans, for example. And then it kind of also matches up nicely with the endpoints. So we can use this to show that there's no surjection from any hSet into the product of countably many circles. So yeah, so first of all, we kind of take B prime to be the kind of family of types defined by the homotopy fibers. So this gives a family of types, so it's a fibration in cubical sets. So this is a map from B prime into the product. And then by definition, in order for this in order for F up here to be a surjection, by definition, we have to have a section of the map from the truncation into the product of circles here. That just because that's kind of unwinding the definitional surjection. Okay, so now we define a family of paths in the product of circles. So we're given, as a parameter, we're given alpha in n infinity. And then we need to define a map from I into the products of circles. And just kind of rearranging the variables. This means we need to kind of define an element of the circle for every I in interval and every n natural. And then we just take it to be, so this base is the kind of base point of the circle, and loop is map from I into the circle, which is just kind of the loop path constructor. So if alpha n equals 1 for this input n, we look at loop and evaluate it at I. And otherwise, we just kind of constantly take everything to be the base point. So if we set alpha to be infinity, then this situation where alpha n equals 1 is never going to come up. So we're always going to be in this case with the base point. So I doesn't play any role in the definition in that case, which means that P infinity has to be degenerate. On the other hand, if alpha is equal to underline n for some n, then it's definitely not degenerate. So in fact, we can take this this path in the circle, in the product of circles, and then we have a map from the product of circles into the circle where we just evaluate at this n, and then we compose it with Pn, and then we get the loop back. So that's definitely not degenerate. So now we consider the path. So we have a path into this product, and then we can compose it with a section, this section S, to get a path in the truncation. So this is the S composed with path of alpha. It's either squash-free or not squash-free. So kind of varying this over the parameter alpha from n infinity, this gives us a well-defined function from n infinity to 2, defined like this. And it has to be continuous by Brouwer's principle. Since P infinity is degenerate, so is S composed of P infinity. Degenerate paths are squash-free, so F has to be 1 at infinity. So therefore, for sufficiently high n, we have that Fn is also equal to 1. So we have one of these non-trivial, non-degenerate paths is also squash-free. So because it's squash-free, we can detruncate it to get this overline map into B primed, and then this commutes with Pn. And then earlier we saw that we defined Pm so that we have this commutative triangle with a loop over here. Okay, and then finally this allows us to get a contradiction. So we have a loop up in B primed, but B primed is an hSet. So because of this, we can contract the loop down to a point via homotopy that keeps the base point fixed. But then we can take this homotopy and then apply it to the maps to move it down into S1. And then that gives a way to contract loop down to a point while keeping the base point fixed. But then that's provably false in homotopy type theory. So we've got a contradiction and then showed that there must be no such B and hSet together as surjection into the circles. So then by by the same kind of argument, but kind of combining it with some like other tricks, we can also get show that a kind of Escardo and Knapp variant of fullness is false, and also a kind of Escardo and Knapp version of collection. And because of this, they're not provable in homotopy type theory. And yeah, and then for like kind of proof theory reasons, when we want to show they're not provable in homotopy type theory, you can actually drop the assumption of Brouwer's principle. So for this kind of non-provability result, you don't have to believe that Brouwer's principle is true, you just have to believe that it's consistent, and it is. So yeah, so we can use this for independence results without assuming Brouwer's principle. And then as a corollary, we can show that various other principles are false. So I've got a few examples here. So this is called the presentation axiom. So this is also called enough projectives, dependent choice, WISC that I mentioned earlier, that the product of circles is connected, Bridges-Witchman-Schuster choice, countable choice from n to the Booleans, and Escardo-Knapp choice. And the reason that these are independent is that you can prove all these implications internally in type theory. So the ones marked red were the ones in the theorem, and then we have all these other implications kind of internally in type theory. So all these other principles have to be independent as well of homotopy type theory. We can also apply this to set theory. So in set theory, in HoTT, okay, there's two interpretations of set theory. So there's Axel's, so this original definition by Peter Axel, where we saw that we got all of these axioms for free, without assuming them, like in the background. But there's another interpretation in the HoTT book, which is defined of set theory, where we define the kind of cumulative hierarchy as a higher inductive type. And there's a kind of a nice presentation of that by Håkon Gilterud. So he showed that we can view that the HIT cumulative hierarchy as a kind of retract of the Axel cumulative hierarchy, which is a kind of a very nice definition and kind of very useful for these kind of results. Yeah, and then so we interpret set theory into HoTT, and then we kind of show these, and then we interpret HoTT into cubical sets, and then we show that these axioms fail in cubical sets, and then so they fail in the HoTT cumulative hierarchy inside the model of HoTT, and then so they also have to fail for they also have to be independent of this CZF with fullness replaced with exponentiation and collection replaced with replacement. So then we kind of remember that it was kind of, in some cases it was kind of very difficult to show that these things were kind of independent of kind of constructive set theory, but like somehow in cubical sets this somehow happened accidentally, that like the model wasn't kind of supposed to be this way, and then for a long time I assumed that that countable choice was true for cubical sets, that it held in cubical sets, but it actually turns out that all these things are kind of false if you assume Brouwer's principle. Yeah, so it's kind of a couple of open problems. Are there any other applications of homotopy type theory to constructive set theory? So I'd be interested in this, and maybe there are also applications to classical set theory. I'm kind of less sure about that, but I'd be interested if there if there are any. So as far as I know, it's still open whether there's a constructive model of countable of homotopy type theory where countable choice holds, and kind of more philosophically you might ask, is countable choice a reasonable axiom for constructive mathematics? Like, should we be assuming countable choice in HoTT or not? So yeah, thank you for your attention.
Thank you, Andrew. That was great. So like we've been doing recently, we're going to visually applaud rather than unmuting just because it messes up some microphones. So let's do that now. Okay, and now we open the floor to questions. If you have a question, just unmute your mic and go ahead and ask. Okay, I will get the ball rolling then, since everyone is shy today. So just to make sure I understand what happened at the end of your talk there. So you mentioned that there are a bunch of independence results in set theory earlier, and you said that they have these difficult proofs involving special versions of forcing. And are you recovering those results in a simpler way, basically? Or at least some of them?
So in some cases, it's kind of, yeah, so in many cases, it's not exactly the same result because, yeah, so for example, for the kind of Friedman-Shedrov proof that collection is false, they weren't working with CZF with exponential, they weren't working over this CZF with E and X. They're working over a stronger theory of IZF with replacement. So that result is actually kind of stronger. So we don't quite get exactly the same result. It is a bit weaker, but I still kind of found it still found it interesting that even for this weaker theory, it's yeah. So also for this weaker theory, it's kind of still even there tricky to show these independence results. Mm-hmm. So I was kind of quite surprised that it just happens in cubical sets.
Mm-hmm. Okay, thank you.
One question from Stockholm, if I may.
Yeah.
So, just wondering about a twist on one of the things you gave. You were justifying the idea of looking at the countable product of circles not being covered by a set as saying it's the simplest place where it could, because it's the simplest non-set and the simplest non-finite thing you could take the power of it. So another very simple non-finite thing is the semi-decidable H-props, the bracket alphas that you looked at earlier. Mm-hmm. So if you took the power of the circle by one of these bracket alphas, would the similar arguments apply there, do you reckon?
Yes, yeah. So I'm kind of still in the process of writing up, kind of working out the best way to formulate these results and the proofs. But in the current version, that is actually how I do things. So instead of the proof that I show today, I show that if the product of countable circles is covered by an hSet, then so is the product of brackets alpha circles for every alpha, and then show that this fails in cubical sets. So in a way, the argument's actually slightly more straightforward, but I found it like a bit less intuitive, so I didn't include it in the talk.
Okay, more questions?
Oh, I'm more from this side.
Okay.
So another very slight variation on these principles is one that Penric, Voschel, and I were led to consider in a paper, which was instead of WISC, you have WIC, a single and weakly initial cover. So it's just like WISC, except it's slightly simpler state because you have a single weekly initial cover. And this doesn't seem to be considered much, but also, as far as we could find, didn't seem to be equivalent to any of the standard ones. So,
it sounds like enough projectives, but I'm guessing it's
right. It's close to the presentation axiom, but it's not, or at least as far as we could show, it didn't seem to be equivalent to it. If I'm remembering right, we couldn't separate it from the presentation axiom, but we also couldn't see, and the people we ran it by couldn't see that it was.
Mm-hmm.
So I guess, Rick, do you have any idea off the top of your head whether these how that would play in?
So I guess it implies WISC, right?
Right, it implies WISC directly. So I guess, right, the independence results for that would give this as a corollary.
Yeah.
Yes.
Okay, more questions? Okay, I'll ask another. So I like that you're also able to get that certain things in HoTT are not provable from these techniques. Do you have any ideas of future things you might be able to show are not provable? And there's various things people are working on that they keep on getting stuck on. You know, showing that the suspension of a set is a one type, or constructing some special types, things like that. Do you think you might be able to handle some of them?
Okay, so you mentioned the suspension of a set being being a one type. Yeah, so this is something that I was kind of a bit hopeful about, and I was kind of thinking that these methods might be useful for that kind of approach, but also it's something that I've tried and I haven't had any luck with it so far. Yeah, so basically I'm a bit hopeful, but I don't really have any solid reasons to believe it works for that yet.
Mm-hmm. Okay, thanks. Okay, anybody else? Got time for some more? Okay, well, if not, then we will again thank Andrew for that talk. Okay, and so that's it for this week. And in 2 weeks, we have Benno Vandenberg speaking. I hope to see you then.